Hello, today I'm going to talk about my research topic in this presentation. So my research topic is about using HBN as a cable layer to improve the reliability of ultra-low K dielectric material for CMOS interconnect. So here is the outline of my presentation. So first I'm going to give a background about the low K dielectric material as a solution to reduce the interconnect capacitance. And then for the first main part is about the process fabrication of low K dielectric material using CNT as a template. And then for the second main part is about the improved reliability of low K dielectric using HPN as a cable layer. And for the third and last main part is about the integration of low K dielectric material with copper for interlayer dielectric. And finally, it is a conclusion about my presentation. So first, here we explain why do we need low K dielectric material. So the continuous with a continuous scaling process for the CMOS technology, the transistor density is increased and the complexity is also increased, and the interconnect density is increased with the continuous scaling, and this increase in the interconnect density requires a reduction in the metal line length and also the electric thickness, and both they increase the metal line resistance and the electric capacitance, and the overall RC delay is increased. So for the ultra scale technologies, the RC delay is even higher than the transistor delay. So to reduce the RC delay, we can reduce the resistivity of the metal line or to use a lower K dielectric material. So aluminum has been used in the past for the metal lines, but it has been replaced later by copper because copper has a lower resistivity and it can reduce the RC delay. But copper is widely used in the material technology even up to date. So it is more difficult to replace copper with another metal. So the most common approach is to use a lower K dielectric material. And there has been a requirement by the ITRS to have a lower dielectric constant during the years with development in the CMOS technology, as shown on this graph. And it is this requirement is continuous. So even for future technologies beyond 2019, we still need a lower K dielectric material. So we need an ultra low K dielectric material for the future technologies with a dielectric constant lower than 2 to meet the requirements for the technology scaling. So on this graph, we show that different kinds of low K dielectric material have been used for different technologies, like the dense low temperature oxide, the FSG, the SiCOH, and for the 45 nanometer and beyond, this technology, porous dielectric has been used with different amount of porosity as spherical pores, as shown here, to have a lower K dielectric material. But this technology has a serious drawback because the spherical amount of porosity as spherical pores, as shown here, can degrade the mechanical strength because it has a random nature. So this can form a short path of spherical pores, as shown here, and this causes elastic modulus to be reduced and the mechanical strength is degraded. So any applied stress to this material can cause failure, and this limits the amount of porosity that we can add into the electric material. So a study has been done to replace this kind of electric material with another material with cylindrical air pores, as shown here, instead of spherical air pores. And with a simulation, it shows that the elastic modulus is higher for this one, and the mechanical strength is higher. So this can increase the amount of porosity that we can add into the electric and stay in the safe limit for the mechanical strength. So we can have a lower K dielectric material and still have better mechanical strength. So this dielectric material can be fabricated using these main fabrication steps. So first, we grow CNT carbon nanotube as a template with vertical alignment and high quality CNT. And then we deposit the silicon oxide to fill the gaps between the CNT as shown here. And then the dielectric can be thinned down using chemical mechanical polishing to reduce the thickness. And finally, the oxygen plasma is used to etch the CNT, leaving the cylindrical air pores as shown here, which we need. And then a cable layer can be deposited onto the low-K dielectric. But this technology still has some challenges. The first important one is about surface roughness. So surface roughness is a serious issue for advanced technologies because for the lithography resolution in advanced technologies, we need surface roughness in the range of 5 to 10 nanometer. And also, if we have a rough surface because of the air pores on the surface, later when we deposit the copper will have some bending into the air pores, and the surface roughness also of the copper will be high, and this will increase the resistance of the copper layers. So the surface roughness of the low-K dielectric is about 80 nanometer, which is extremely high, so it has to be reduced. And then for the second challenge is about the copper diffusion, because if we have a metal via as shown here, copper can diffuse from all sides into the low-K dielectric, and this diffusion of copper atoms can form a short path for the current to pass through the electric material, and this will cause breakdown and will reduce the failure time. So this is another serious issue that has to be solved to increase the failure time and prevent copper diffusion. So HBN has been used for several studies to improve the reliability of LTO, dense LTO, low temperature oxide, and it has been successful to work as an electromigration barrier to increase the failure time and prevent electromigration. And also it can reduce the copper diffusion into the LTO and increase the time-dependent dielectric breakdown.